Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, continuing on last week's video about roller coaster physics and an introduction to energy. Quick review of the topics there. Right, if you want to have the full video from last time, I have it linked down below if you want to check it out there. But the key idea is thinking about energy. Kinetic energy is the energy of motion, an object in motion. We have kinetic energy as 1/2 mv squared. Now, we're not going to focus too much on units here. Just want to kind of remind people that mass is typically in kilograms. When we're talking about velocity, that's typically going to be meters per second. You could change these things, get different units, things like that as well. We also have potential energy. So potential energy measures energy that can be converted into other forms of energy. And we talked in last week's video how this is relative. So for gravity, the change in potential energy is mg, change in the height, right? M is the mass, g is acceleration due to gravity, delta h is a change in height, right? Shouldn't surprise you here if we're using meters per second squared. Height here is going to be measured in meters in this scenario. Now, one thing I want to keep in mind, and we'll mention this on the next slide as well, but notice that the mass appears in both equations. So we're going to be setting these equations equal to each other, right, and kind of working with stuff that way as well, but the mass will cancel out. So I'll just say the mass is 1 on the next slide, but if we had a different mass, you could also think of that as the calculations in the end, those masses would cancel and we can go from there. So let's talk about our question from last time then. Right, so suppose we have 4 heights given in a roller coaster, and right, we want to know the speed at the 4 points. Now, we mentioned in last week's video, let me remind you of that as well, right? We need to make some sort of assumption, but it's better to think about this in general. You could, as a challenge question, think about other versions of this. Think about the case where at the highest point, that roller coaster is not moving. Right? Of course, maybe it moves a tiny bit to go over the hump and then starts falling down, but we can assume that that speed at the top is 0 meters per second. Now, let's explore how to use this idea of energy to go through this question there. So we have our roller coaster and we have the different heights that were given in this scenario there. Now, a little bit of bookkeeping here. Remember I said that the masses will cancel in this case, but let's just assume that the mass is 1, just so I can write out things here as well. Now, reminder, our potential energy, and let me just write this out, mgh, right, which is just going to be gh with our m equals 1, right? This is going to be relative to the ground in this scenario. You could do this relative to the different parts, but I want to make a little bit of a chart in this scenario there as well. Also want to remind us that G is approximately 9.81. I have the numbers, but if you just want to double check those numbers later as well. And our last piece here is reminder of the kinetic energy, 1/2 mv squared, which, because mass is 1, just 1/2 v squared in this scenario. Now, what is our key idea in this scenario? Right? Our key idea is the energy doesn't change. So let's kind of make a chart here, and we'll talk about that energy doesn't change bit in just a moment here too. But right, we have our different heights in this scenario, and let's start thinking about the different quantities we want to look at, right? So we have the heights. That's going to allow us to find the potential energy. And then, right, we have kinetic energy that we're also thinking about, and then we have velocity. Now, let me do this a little bit weird, right? So let's say potential energy, total energy, then I'm going to write kinetic energy, and then I'm going to write velocity. Now, why am I doing it this way? What's the kind of strategy here, and what's with this somewhat weird ordering that we have? Well, let's think about that first point that we have. Well, we know at that point, right, at this point at the top, our assumption was that the velocity is 0, meaning the kinetic energy is 0. So if we talk about the potential energy, right, 9.81 times the height times 50 meters there, right? These are all going to be approximate in this case, but let's say we have roughly 490.5, right? That's roughly 9.81, 98.1 times 5, 490.5. Now, the key thing is that this total energy here is all that potential energy. There's no kinetic energy. So that tells us that those two things have to add up to the total energy. And our key idea that I was getting at in the problem is that this total energy is never going to change. So if we highlight that bit there, all of these cells are going to be 490.5. That's what we're going to have for every single case there. And this is our idea of that potential energy being changed into kinetic energy in this case. But now we can start looking at these at different points. And the idea is going to be similar, but let's talk about the first one a little bit more carefully. So potential energy there times 5, right? Well, times 9.81, 490.5, we're going to have 49.05 there. You can decide how many decimals you actually want to use. But if that total energy is 490.5, we're assuming here our key idea is the rest of that energy is kinetic energy. So we have 441.45 there. And now let's show the work there for this, right? So for this one, I'll show the work, and then we'll kind of skip it for others. 1/2 v squared is supposed to be that kinetic energy. Remember, we're assuming m equals 1, so we have 441.45. Multiply by 2, square root, the velocity is approximately equal to 29.7 in this scenario. Double the kinetic energy, take the square root, 29.7 here. And notice that this same idea can be used for the other points. So let me do these a little bit quicker. At 3, it's at a height of 40 meters, right? So at that position there, right, we can say this is 392.4. Well, what's the leftover kinetic energy? We're now going to have a leftover kinetic energy, right, of 98.1. Not that much there. And velocity, double that, take the square root, you're going to get roughly 14 for the velocity in that case. And we could complete this for the final point 4 there as well. So here at this point, right, we're a little bit lower, 294.3. Our kinetic energy there is going to be, right, we're at 30 meters here, so we are at 196.2 in that scenario. And right, that's our change of height of 10 meters, and this velocity is roughly 19.8 there. So by using this energy, we actually have a pretty quick way of coming up with all of our velocities pretty quickly, right? We just find the kinetic energy. If you were doing different points, maybe you wouldn't find all of the potential energies. You could use relative, change in potential energy, different things there. But for all of these put together, it's nice to have this chart with this total energy not changing. Now, after saying all of this, let's look at our question there, right? The speeds in real life would actually be a little bit lower than what we calculated just now, right? So if the speed is lower, right, of course, now this should be pretty obvious. The kinetic energy is lower, right? So the kinetic energy is going to be lower in this case. So let's cross out that higher and highlight the lower here. Now, what might be a reason? So we did the math. Okay, if the speed is lower, squaring it, dividing by 2, multiplying by the mass, that's lower. Why might this actually be lower in real life? And we're not going to talk too much about this here, right? But the short answer there is, right, there are other types of energy. So the potential energy gets turned into, right, other types of energy. Or kind of, you might say this in other ways of this as well, right? I'm putting this in quotes, but this is a real physics word, right? It does work. That potential energy is doing something else rather than just being turned into kinetic energy. So some of that potential energy goes to kinetic energy. Most of it, right? The calculations we did are not horrible. This is a very useful thing. That's actually going to be fairly accurate, and this is probably how people would at least start doing these calculations in the real world. But in reality, it's a little bit lower. You have different frictions, sound, heat, these other types of energy. That potential energy is not all converted into kinetic energy there. That will be a good place to stop here. We will have a new topic next week. If you're interested in some of these physics topics, we do have our summer term coming up. We have some physics courses there as well. You could check out to learn more there too. Otherwise, let us know if you have any questions or ideas for future topics in the comments below. Give us a like if you enjoyed the video, and I will see everyone next week. Goodbye.